Um, Hello everyone, welcome back to the DDLC seminar series organized by the IDS Lab at Cornell University. And this is Nishant, and it's a pleasure to introduce today's speaker, Professor Peter Seiler, and he's going to give a talk about robust online convex optimization for disturbance rejection. Why about Dr. Seiler? Dr. Seiler is an associate professor in the Department of Electrical and Computer Science Engineering at the University of Michigan, and prior to this, he worked with Honeywell Labs, and he was a principal scientist from 2004 to 2008 in the Aerospace Electronic Systems Group. And during that time, he worked on redundancy management systems for Boeing 787 sensor fusion algorithms and also the re-entry flight control laws for the NASA's Orion vehicle. And his research interest spans on robust control theory, addressing the impact of model uncertainty on system design, and has been a contributor to the robust control toolbox in MATLAB since 2001. And Dr. Seiler is an IEEE fellow and is also a recipient of the Hugo Schuck Award in 2003, as well as the Brockett Williams Outstanding Paper Award in 2020, and he has also received an NSF Career Award in 2021. Without further ado, I'll let Dr. Seiler take on. Thank you.
Awesome. Thank you for the introduction and thank you for the invitation to speak today. I'm going to talk about some work that was done jointly with my student Joyce Lay. So this is primarily her contribution. And so it'll be online convex optimization, kind of blending in some robust control techniques. And the optimization that we're going to think about, and I'll give a kind of a more detailed problem formulation in a moment, but the basic idea is we're going to think about disturbance rejection. So this is really for applications where you have high precision control. So we're going to talk about satellite pointing as being one issue or one potential application. And when doing this type of learning, we're going to note that small model errors can lead to instability. So what we're going to try to do is blend some learning with some techniques to bound the impact or be robust to model error. And I've given kind of the two recent papers. One's a 24 CDC paper that was presented last December, and then the second paper will be presented at the ECC this summer. And then I should acknowledge that this is being kind of supported off of an NSF grant. Okay, so the basic idea is we're going to talk about optical communication for satellites. So I'm going to just talk a little bit about this problem formulation, and this will motivate, why we might want to do online optimization. So here's the basic idea. You've probably seen in the news different types of using constellations of satellites to beam internet or beam communication anywhere in the world. And so Starlink is the maybe the one that's most common. Just in the last few days, Amazon has launched their first, I think, 27 or 28 satellites. Similar in concept, but basically they're satellites in low Earth orbit, somewhere between 550 and 650 kilometers. And basically you form a mesh network and you can beam to anywhere in the world. And let me just talk a little bit about the basic operation. There's quite a bit of this that's in the public kind of literature or that you can find, data on. And so I'm going to talk a little bit about the Starlink kind of configuration. And so the basic idea, this is, the initial concept from 2020. They were approved for 7,500 satellites, and the data was basically, stovepiped from a starting point up to a satellite, back to a ground station, and kind of back up and down again. And that was the initial kind of concept. The beaming was in a 10 to 30 hertz, gigahertz, I should say, bands. Last year, I guess this is, last March, they had approval for another 22,000 plus satellites. And they had some approval to also do Earth to satellite communications in the 70 to 80 gigahertz range. Now, ideally, you'd also like to be doing the following. Rather than doing this stovepiping, you'd rather communicate up to a satellite and then communicate satellite to satellite all the way back down to the end. And the reason why you might want to do that is there's maybe a couple reasons, but the main reason is that you have lower latency. So if you're communicating, in space, satellite to satellite, you have much lower latency than either doing terrestrial kind of communications or doing this kind of stovepiping where you're communicating through the atmosphere. This is actually much more difficult, and we'll talk about why this is. And so, Starlink, they launched their first satellites in 2021 to do this. Kuiper did a version of this in 2023. the communications that are in the satellite in space, those communications are not entirely clear. And the reason why is when you're communicating from the satellite to the ground or vice versa, those are, those kind of links are covered, that spectrum is allocated. And so the FCC kind of governs that in the US. And so there's public documents that describe kind of what those frequencies are. The frequencies that are going to be used in space are not covered by the FCC, at least that's my understanding. So you can't find kind of clear documentation of what frequencies they're using here. But the most plausible range is in the hundreds of terahertz range, so much higher frequencies than are using ground to satellite. Now, why optical links? And so when I say optical links, if I back up one slide, these optical links from satellite to satellite, why are they operating at such a high frequency, 200 terahertz? And I'm just going to give you kind of the basic physics of why they work this way. So if I have a beam that's coming from one satellite and I'm trying to aim it to another satellite, basically they're diffraction limited, meaning the beam is going to spread out. And that divergence angle depends on the frequency that you're communicating at. And it depends on the width of this aperture. And so the frequency here, or the wavelength of that, is governed by this equation. The wavelength times the frequency is the speed of light. So the basic idea is you go up in frequency, you have smaller wavelengths. If you have a smaller wavelength, you have a smaller divergence angle. Now, so that's the reason to try to be at a very high frequency when you're doing these links. Now, what's the benefit of that? The benefit is because the divergence angle gets smaller, you can transmit with lower power because you've got a very kind of small beam and you can direct it more finely to the satellite that you're communicating to. That also improves signal to noise ratio, so it gives you higher data rates. It also means you can use a smaller aperture width here, so your transmitter can be smaller, so you use kind of less weight and volume. And then also, if you have a narrower beam, you might be concerned about security issues. And so if you can beam more directly to the satellite that you're interested in, you maybe have less concern about interference from other satellites or maybe, security issues of somebody intercepting your communications. Now, what are some of the satellites? What are some of the issues with doing this? For satellite to satellite communications, so this is just kind of a quote from one of the Amazon press releases. Basically, you have to maintain links between two satellites. They're basically, several thousand miles away from each other, 2,600 kilometers. They're traveling extremely fast relative to each other. And you have all the dynamics of the satellite, flight dynamics, and the transmitters that are on the satellites are shaking. And so it's a very hard problem to maintain this link. So let me give you just maybe some concrete numbers just to explain why this is complicated. The satellite receiver is maybe about a quarter of a meter. We're communicating at a distance of about 2,600 kilometers. So if you want to aim a beam and hit the receiver on the other side, and the receiver is about a quarter of a meter wide, you can calculate just from the simple geometry what your divergence angle must be. And so there it is in radians, or it's 0.01 arc seconds. And so NASA's got a report on like different types of problems for, space missions. In this case, it's optical communications. They would state that something with this level of accuracy, you're going to point to 0.01 arc seconds. That's a very difficult and risky problem. And in their report they say you may even require cherry picking components, meaning on the satellites, you've got actuators and sensors. You may have to buy 10 of them and just pick the best one so that you minimize all the deviations due to manufacturing tolerances and so on. If you want to give it maybe another interpretation, this is kind of centered on Ann Arbor. Out here in Boise, that's about the distance of what the satellites are. You basically need to put one satellite here, aim the beam so that you hit a basketball on the other side. Okay, everything on here is basically of the same distance. So Ann Arbor to Phoenix or Ann Arbor to Calgary, that's kind of the level of precision you need to be aiming. Is from here to any point on the circle, be able to hit a basketball. So now let's kind of get down to the level of, the control problem. There's many feedback loops that are required on a satellite to do this kind of pointing. So this is maybe showing a kind of one version of these type of satellites. You've got the solar arrays sitting out here. Sitting on top, you've got the transmitter and receiver box. So So that's kind of zoomed in here. So you can either transmit the beam or you can receive the beam from another satellite. The various feedback loops are, there's a kind of a crude pointing loop for the satellite that you want to point in a particular direction. This transmitter receiver box has also got kind of gimbals on it that it can be used for pointing. And then we're going to get down, there's even a more fine grain kind of pointing loop. So all this is to tell you there's kind of like, it's a hierarchical level of cascaded kind of control loops. If I zoom down into this gimbal, though, so this is now kind of taking a cut through of this gimbal that I had on the previous slide. What you have is something that looks like you've got a little gimbal here that kind of does the more fine precision pointing. You have data that's coming in and out. So, for example, data that's coming in from another satellite hits a primary mirror. It then points back into the inside the gimbal. Inside of there, there's what are called fine steering mirrors. Those then point the beam onto another mirror that will then go into the transmitter. So that last little bit of like pointing accuracy is as the beam is coming in, this mirror is kind of constantly adjusting slightly so that the beam then kind of lands on the center of the transmitter. These are usually 2-axis mirrors, so you're rotating them about 2 axes to get the kind of last high precision pointing. This is the piece that we're going to focus on, is that very last high precision pointing of the incoming beam. But the thing you should be aware of is, this is all sitting on a spacecraft. The spacecraft itself is trying to do its own pointing. The gimbal is trying to do its own pointing. Those are all creating little, what we call small micro vibrations that are making it more challenging for this mirror to do its kind of last little bit of pointing accuracy. Okay, that's the motivation. Now I'm going to get this down to maybe what we would think of as like a more abstracted version of the problem formulation. And so if you abstract all of this away, it looks like a more classical control problem. There's disturbances. We have this pointing model or this mirror that's doing the dynamics for the last little bit of pointing. All the disturbances are coming about, again, because the gimbal's sitting on top of a satellite. It's got its own little vibrations that are shaking the mirrors a little bit. And based on the dynamics, the y is the measurement of the beam in the center of some transmitter, which is really a two-dimensional measurement, but we'll think of just the one-dimensional case. And our goal then is, at this abstracted level, is we basically want to reject all these micro vibrations. These are non-stationary. There's a little bit of like white noise disturbance, just, broadband noise. But there's also parts of the disturbance that are, I would say, repeatable. So on the main part of the satellite, there are what are called reaction wheels. Those start spinning up, and they're helping the satellite do the crude pointing. When those reaction wheels spin up, they create very strong disturbances on this fast steering mirror, but at some frequency that we don't know ahead of time. So the main point here is the disturbances are non-stationary. We don't know them ahead of time, but they do have things that we can learn. There are repeatable features. There's harmonics in them that are strongly affecting the performance. Our goal is basically the following. I tell you the plant. We're going to see that the model of the plant has got imperfections in it. So we don't know the plant model perfectly. We might know basically what it is at low frequencies, but at high frequencies, it's got model errors. And our goal is to try to reject these disturbances. And what we're going to see is there are some fundamental limits of how well you can do this just with classical control. So if you just do linear time invariant control, there's some limits on how well you can reject this disturbance. If you're willing to modify or update the controller online, this is the learning piece, you can do a better job of rejecting the disturbances. That's going to be the key point here. And so our goal is to make the variance of the output as small as possible by designing this controller. And I've motivated this from the standpoint of satellite control, but any other problem that has like very high precision requirements, hard disk drives for cloud storage would be one, photolithography, those would be other types of applications that would have these kind of similar stringent performance kind of characteristics. So let me just briefly talk about the fundamental limits here, because this will motivate. And when I say fundamental limits, I mean fundamental limits if you're just going to use linear time invariant control. This will explain why this is not enough, maybe in learning is a suitable strategy for this type of problem. So I'm going to just kind of review a few things that are just maybe classical controls related. The transfer function from disturbance to output, That's the sensitivity transfer function. So that's 1 over 1 plus the plant times the controller. Let's assume that the disturbance is stationary. And so it's zero mean. And let's say I tell you what the power spectrum is. So the power spectrum tells you the energy of the disturbance as a function of frequency. So if it was a pure harmonic, you can think of it conceptually as like an impulse at that frequency of the harmonic. If it's white noise, then the spectral density is flat across frequencies. But in general, the disturbance, in the practical setting, the disturbance will have large energy in certain frequencies that we don't know ahead of time, and then it'll have maybe some broadband noise. And the question is, what's the minimum variance that output that we can get just by using linear time invariant control? This can actually be formulated just as an H2 optimal control problem. So if you told me the plant and you told me the power spectrum of D, I could then formulate what's the exact optimal controller for the controller K to do this kind of minimum variance problem. I'm not going to formulate this as an H2 optimal control problem. I'm going to derive an analytic expression. So the benefit is you'll be able to see what's the trade-off here and what are we limited by in terms of the performance. So here's the kind of basic sketch of the idea. If I tell you the power spectrum of the disturbance, and it's zero mean and so on, then the power spectrum of the output is just the sensitivity magnitude squared multiplied by the power spectrum of the disturbance. So the sensitivity is really what's transferring energy from the disturbance to the output. And then if I ask you what's the variance of the output, it turns out the variance of the output is just you can integrate the energy in the power spectrum of the output. Okay, and I've kind of scaled things here by only integrating over half the frequency axis. Now just substitute in for the power spectrum of the output, and you get this expression that depends on the power spectrum of the disturbance, and it depends on how you've designed your controller. So ideally, you would just design the controller so that the sensitivity is less than 1 at all frequencies. Because if this sensitivity has magnitude less than 1, you're kind of attenuating the disturbance spectrum at that frequency as it's passed to the output. However, it turns out there's always going to be frequencies where the sensitivity is bigger than 1. Turns out you're amplifying the disturbance. The reason why that is there's this fundamental constraint with linear time invariant control. And so just to quickly talk this through, suppose the plant is stable and the controller is just 0. So I don't do any control at all. So if I don't do any control at all, the sensitivity then is just 1 divided by 1. It's 1 at all frequencies. If I plot the log of the sensitivity versus frequency, it's just 0 because the log of 1 is 0. And if I don't do any control at all, the variance of the output will just be the variance of the disturbance. So the point here is if I don't do any control at all the disturbance is passed to the output, and I haven't done any kind of sensitivity reduction. Now, ideally, when you do control, the sensitivity looks something like this. It's small at low frequencies. You're attenuating the disturbance. Then it tends to have a little peak bigger than 1. You're actually amplifying the disturbance, and then it goes to 0. And the reason why that you're amplifying the disturbance at some frequencies is that follows from the Bode sensitivity integral. The Bode sensitivity integral is basically going to say if you are improving or reducing the effect of the disturbance at some frequencies, you must be degrading it at other frequencies. This is a consequence of linear time invariant control. So just to quickly recap that, the Bode sensitivity integral just says if the plant is stable and the controller is stable, okay, so the loop has 0 poles in the right half plane, and let's say the closed loop is also stable, then if you integrate the log of the sensitivity at all frequencies, you just get 0. And so there's maybe one more technical assumption, which is the loop has to have relative degree 2, but that basically always happens in practice because the plant has to roll off at high frequencies, and so does your controller. So the point of this sensitivity integral, this is like the control version of conservation of energy or conservation of mass. These conservation of momentum, conservation of energy in physics, right? We have these conservation principles. In controls, this says there's a conservation of sensitivity. If you make the sensitivity less than 1 at some frequencies, it has to be bigger than 1 at other frequencies. And when you integrate it all up, it has to balance out to 0. Now I'm using the natural log here. It turns out the natural log is just a scaling constant from just sensitivity in units of dB. So this is what I would say is the key conserved quantity in feedback design, and it's really the fundamental restriction with using linear time invariant control. If you use linear time invariant control, you're going to improve performance at some frequencies, but it's going to come at the expense of increasing or degrading the performance at other frequencies. I'm going to skip over this. This just gives a little more details about, how this comes about. So I'm going to use this now to explain why we can't, or what's the fundamental performance limit in this kind of abstracted version of our disturbance rejection problem. Okay, so let's come back to our disturbance rejection problem. We've got a disturbance coming in. The sensitivity is the transfer function governing the transmission from disturbance to output. And I want to find out what's the minimum variance I can get in the output if I use a linear time invariant controller. So I can formulate that in the following way. Here's the variance in the output, right? Because we said the variance in the output is just the integral of the power spectrum of the output, but the power spectrum of the output is just the power spectrum in the disturbance multiplied by the sensitivity. But whatever the sensitivity is, it has to satisfy the Bode sensitivity integral. And the one slide that I skipped is, it turns out for practical reasons, the Bode sensitivity integral has to be approximately satisfied up to some, what I'll call available bandwidth. Think of that as you've got, you implement your controller with a certain sampling rate. Then from the Nyquist stability, like the Nyquist sampling theorem, there's some frequency beyond which you just can't do control. So there's usually an upper limit beyond which the loop just has to roll off. And so the Bode sensitivity integral has to be satisfied over some kind of finite frequency range. And then above that, the sensitivity is just 1 because the loop is approximately 0. So this is the optimization. Now, it turns out you can solve this optimization, semi-analytically, and you can find out that the optimal variance, the minimum variance you get, basically breaks into two pieces. So without worrying too much about what the equations, the form of the equations, the two pieces are, there's a piece of the disturbance that you cannot reduce because it's outside the available bandwidth for which you can do control. Like once you set the sampling time for your controller, there's a certain frequency range over which you're not doing control, and you just pass through the disturbance of the output. The other piece, though, is what's happening in the range that you're doing control. And it turns out you can get some sensitivity reduction or disturbance reduction in that range. And so the minimum variance that you can get in that range depends on the bandwidth over which you can do control. So if you can have a higher available bandwidth, which means you have better actuators, faster sampling, you'll be able to do better control. This term here you can show is lower, or is a lower bound on what would have happened if you did no control, meaning you're actually going to get some benefit from control in this range. So this expression here tells you how well you can possibly do with any linear time invariant control. Now, it turns out if the disturbance is just pure white noise, this first term ends up just being this upper bound. And when you kind of simplify all this together, what you get is the variance in the output is just the variance in the disturbance. So this is maybe some useful insight. If the disturbance is white noise, there's kind of nothing to learn. There's nothing to, the disturbance is just constantly changing, so that there's no benefit to feedback. You just can't, reject the disturbance. Every time you're seeing a measurement, it's based on the current and past value of the disturbance. That doesn't tell you anything about what the disturbance is going forward. So there's no performance improvement possible. So there has to be some feature of the disturbance that the controller can exploit to improve the disturbance or improve the performance. And generally speaking, if the disturbance is harmonic, if you knew that it was, for example, just a pure sine wave, and you even knew what the frequency is, you can imagine then you can project out what the disturbance is going to be if you know that ahead of time. And then almost like you can do non-causal control. You can anticipate what the disturbance is going to do, and you can do a much better job of rejecting it. So this is ultimately what a learning-based controller can do, is if you know that the disturbance has got some repeatable features to it, but maybe you don't know what frequency it's at, or you don't know the precise details of that, a controller that can try to learn what the disturbance is doing and then almost project ahead what it thinks the disturbance will do can do better than just linear time invariant control, which is just kind of looking at the past and not doing that quite the same projection. I'll skip this. This performance limit is, there's some few more details, but just in the interest of time, maybe I'll move on to the next thing. So this is all kind of just setting up motivation for why you might want to do online optimization or some type of learning. It's again, there are these basic limitations with doing linear time invariant control that aren't going to be, things that are learning or doing time varying control. Maybe you can skirt around these fundamental limitations. Okay, so that's kind of the next piece. Is I want to talk just a little bit about doing this disturbance rejection. And you can think of the way we're doing learning, you can think of them as somehow they're nonlinear or time varying controllers. And I'm going to focus on the case where the controllers are just linear and time varying. So examples are going to include things like recursive least squares, retrospective cost adaptive control, which, has been promoted by one of my colleagues here at Michigan, Dennis Bernstein. And there's a lot of recent work on different types of regret formulations. I would say these regret formulations, they kind of fall, broadly speaking, into two classes. There's one version where the baseline, they try to formulate a control design or a learning problem where you're trying to have the learning be compared against a baseline. If the baseline is the best controller that knows the disturbance entirely into the future, and you allow the controller to be anything that uses the disturbance entirely into the future, you get one set of results which look very familiar to kind of old ell-infinity type results. Those are results by Hasibi and colleagues. There's another set where the baseline is maybe a little weaker. I tell you the disturbance ahead of time, but I only allow you to do maybe the best state feedback that could be designed for the given disturbance. The policy isn't allowed to be dynamic. That leads to a different set of tools where the controllers optimize online, kind of using that kind of baseline as the basic formulation. So there's lots of work here. I'm not going to kind of go through kind of the full literature. I will say one piece of work that, from another student of mine, which I'm not going to focus on, this paper by Liu, where we talk about a plant model where we've got a baseline controller. It has full knowledge of the disturbance, but it doesn't know or doesn't try to learn what the plant is. And we get kind of worst case regret bounds. So if you're interested in that, I'm happy to say more about that. It's more along the lines of the work by Hasibi, where the controllers that we get are linear time invariant controllers. They're not optimized online. Okay, at any rate, let me now kind of transition into a very simple version of online optimization. I'm going to just use classical recursive least squares just to illustrate kind of what some of the issues are. So let's come back to our kind of basic classical loop. Again, we've got a disturbance. The goal is to reject the disturbance in the output. Let's assume I've designed a kind of a baseline controller. You could certainly get rid of this baseline controller, but we'll use this maybe as a starting point. So assume that the baseline controller is getting rid of some of the effects of the disturbance, but we know, as I just described, that there are some fundamental limitations with just doing linear time invariant control. So let's assume now I wrap around this another loop that tries to estimate what's the effect of the disturbance, after you've closed this initial loop. And then based on that, you do recursive least squares to figure out what can I inject in that will cancel the rest of the effect of the disturbance. Okay. So this is the part of the thing that's doing optimization in real time. This is just, nothing special about recursive least squares, just it's a very classical algorithm. In fact, this architecture was proposed kind of 15 years ago as kind of one method to do jitter reduction or reduce the variance in the output when you're doing these optical communications. So how does this work? Well, let's think a little bit more about this. If I, for a moment, don't worry about this input, then the transfer function from D to Y we said is the sensitivity. So the effect of the disturbance on the output after I close this first loop will just be the sensitivity multiplied by D. I'll call that kind of signal W. This is all in the Z domain. So W, think of as the signal left over after you've approximately canceled or attenuated the disturbance in this inner loop. Then I'm going to inject a new signal V, and the transfer function from V to Y is what's called the complementary sensitivity function. That's given here. So the output will be the sum of the two pieces. The piece that you've injected in with V, and then the part that's left over the disturbance after you've done this baseline control. Now, what we're going to put here for the recursive least squares, so now kind of switching to time domain notation, is we're going to try to figure out what this signal should be. And we're just going to use an FIR filter. We're going to try to learn what these coefficients should be. We're going to estimate what that disturbance signal was, that W. Again, the W is what's left over after I've closed the initial loop. I'm going to try to estimate that. And then the signal that I'm going to inject in here, I'm going to try to figure out how to use that estimate of the leftover disturbance by updating these coefficients at each point in time. So this is kind of done in discrete time. So this is, what people might call a disturbance action or finite impulse response filter. So these are the coefficients that we're going to learn. Now you can basically say what I'm going to try to do is minimize the variance. I'm going to stack up all the past history of y. I'm going to try to then formulate an optimization to figure out what coefficients would have given me the minimum variance in the past. It turns out that'll just be formulated as a least squares problem. So I'm skipping some details here, but the things you're going to pick are these coefficients at each point in time. The A's and B's are kind of bookkeeping all the dynamics here based on all the past measurements that you had. Now, this optimization is growing in time. Every time you get a new measurement, you're kind of adding more data. The A matrix and the B matrix, you're getting one more row. But you can solve this recursively. So you can solve for the global optimum at each point in time. And this basically tells me what are the coefficients I would have used given all the data I've collected up until now, and what coefficients would have minimized the variations in the output. You can almost think of this as you're replaying the past history. You've estimated what the disturbance was. Now let's replay what should I have injected in to minimize the variance in the output. So again, you can get the global solution at each time through recursive least squares. Now I'm going to just try to show you how this performs. And again, nothing special about recursive least squares. The main point here is just to try to understand what's the impact of model error if I try to do this. So here's a simple example. I've got a simple plant model. There's a double integrator. You can think of that as like Newton's law, mass type dynamics. And there's a little bit of high frequency unmodeled dynamics. This is like almost like a flexible mode. So when you start shaking these mirrors in the satellite pointing problem, it's almost like a rotational Newton's law dynamics. So there's some rigid body dynamics, but the mirrors themselves, if you collect data, they have a little bit of flexibility in them. So there's some extra dynamics here. The baseline controller is just a PID controller, nothing special about that. The loop bandwidth is about 12.5 radians per second. And we're going to take these continuous time dynamics and we'll implement them at a sample time of 0.01 seconds. I'm going to use this as my disturbance. So I've got kind of a low frequency, 2 harmonics disturbance, and then I've got white noise. Okay, so the variance of the white noise has got a standard deviation of 0.05. So that's the standard deviation of the white noise part. The standard deviation of the whole disturbance is 1.18 when you kind of add all these terms up. The reason I'm pointing out this 0.05 is when we look at how well the controller does, the white noise part is the part that you really can't cancel. There's nothing to learn for this, so you're kind of, that's going to be the basic performance limit. Our hope, though, is we're going to be able to learn the effect of these two disturbances and we're going to cancel them out. Now, the FIR filter, what we're injecting back in, will have 10 coefficients. So those are the coefficients that we're going to learn, and we're going to just be reacting based on our estimate of the disturbance that's left over after the PI control loop is closed. So here's basically how it kind of performs. We're first going to assume that the model, the actual dynamics are exactly equal to the model that we used in the control design. We're going to run a simulation. We'll look at the output versus time. For the first 10 seconds, we don't have recursive least squares on. So we're just doing the baseline PI controller, or I guess it was a PID controller. And you can see the effect of the disturbance harmonics. So the standard deviation of this signal is 0.27. So the baseline controllers reduce the standard deviation from 1.18 to 0.27. That's good. It's done quite a bit of reduction. But the PID controller isn't trying to do anything specific for this particular disturbance. So you can see there's still harmonics left over. At time 10, we turn the recursive least squares on. So that basically has an opportunity to learn what's left over and try to cancel the rest out. So now all of a sudden you see it kind of very quickly learns the remaining effect of the disturbance, almost perfectly cancels out. What's left over has got a variance of 0.06. That's basically the variance of the kind of white noise that was in the disturbance. So you really can't do much better than that. Whatever's left over, you kind of cancel it out all the components that are learnable. And the piece that's left over is just the part that's just white noise. There's nothing learnable there. Now, if you add just a little bit of model error, so this is the design model, that kind of simple fourth order model that I had a few slides ago. But I'm going to simulate the plant by just adding a low pass filter at a very high frequency. And I'm going to run the same simulation. So for the first 10 seconds, it's just the classical PI controller. It turns out this is a very small model error. And for the classical controller, it has almost no effect. This part of the plot is almost exactly the same as the plot on the previous slide. The standard deviation in the output is slightly larger than on the previous slide, but you really don't see much effect of the model error. Now at time 10, you turn the recursive least squares on, and you can see it starts going unstable. And so what's happening is our estimate of the disturbance is now kind of being corrupted by this model error. The estimator has a model of what it thinks the plant is doing. It's using that to estimate the effect of the disturbance. And so that's now causing this whole loop to go unstable. So very small errors are causing the online optimization to go unstable. Well, that wouldn't be true in the classical controller. On the other hand, the online optimization is much better at canceling out the disturbance, whereas the classical controller can only kind of crudely cancel the disturbance. So we'd like to kind of blend these two pieces together. That's the basic idea. So at this point, you might ask the question, well, the online optimization really does a good job of learning the disturbance. It's leading to an instability when I have model error. So why not just learn the model as well? And there's lots of papers where you can try to learn the model error in addition to learning the disturbances. And I want to just maybe comment on why I think that's not so easy to do, at least in this type of setting. So let me focus on this example on the right because it'll have the features that I want to describe. It's a Bode plot, frequency, there's magnitude and phase. The blue are experimental data collected from about 50 hard disk drives. So this was data that was shared by Seagate. It's been normalized for proprietary reasons. If you look at low frequencies, all the blue curves look pretty well clustered together. They're all pretty repeatable. As you go out to high frequencies, all the models look quite different. There's not, there's not much similarity between them. The red is like a typical design model that you would fit. It fits quite well at low frequencies, and then at high frequencies, it's not fitting very well at all. So the thing that I would say here is most models have these kind of features where at low frequencies, and so what you should think about is the frequency axis is almost like a time scale. Low frequencies correspond to long time scales. High frequencies you think about as kind of short time scales. Our models tend to be very repeatable at low frequencies. And so there's, a lot of commonality here. As you go to high frequencies or short time scales, there's lots of variation. There's time variations, there's nonlinear effects. In fact, the models that we have are really modeled, they're structural dynamics. They're really partial differential equations. It's really hard to learn things out here because the dynamics are actually changing in time, and it's, they're nonlinear effects. A lot of the results where you're learning the model also assume maybe you have a finite state dimension. That may be a benign or appear to be a benign assumption that I believe the dynamics are finite state dimension, but really things like time delays, structural dynamics, which are partial differential equations, these are infinite dimensional. There really isn't a finite dimensional model that they'll learn here. So the thing that I'm trying to summarize here is the disturbance spectrum is usually at low frequencies. There's learnable features there, repeatable and learnable features. Dynamic uncertainty or dynamic error contains things that are just not very easy to learn online. That's kind of my claim here. And so I'm going to focus on the following formulation where I still want to use online optimization to learn the disturbance, but I just want to be robust to these high frequency model errors. I'm not going to try to learn the model. I believe the model that I'm using at low frequencies is good enough, but I want to be able to tolerate these little bit of variations in the online learning. So that kind of leads into these kind of robust stability results. So let me just talk a little bit about kind of the core theory of how we do this. Generally speaking, we assume we've got a nominal model. So I'm going to continue kind of using this hard disk drive as an example just to illustrate this. So the nominal model is the red. The actual models are one of the blues. And the way we're going to do this is we're going to think about the nominal model, which is the red, and then we're going to add some error here. So the error will be kind of added on top. And our belief is that any one of the blues can be written as the nominal model red, plus a little bit of error, and how much the error is depends on the frequency. So if you subtract one of the blues from the reds and you divide by the red, think of that as like a relative error, percent error. You can plot that on the right. And what you see is the relative error is very small at low frequencies. Minus 40 dB corresponds to like 1% error. But the model error, relatively speaking, is growing at high frequencies. And so this, alpha is basically representing how much model error is there as a function of frequency. Small at low frequencies, but the models degrade as we get to high frequencies. So the idea is going to be, we know what the design model is. We use the red in our controller. We don't know what the actual dynamics are, but at least we know the actual dynamics are very close to our design model at low frequencies. But as you go to high frequencies, we can bound how much error there's going to be. And that bound is somehow going to tell the controller, hey, you really shouldn't trust the plant model if you're trying to react quickly, because the model is not accurate at high frequencies. But the model is reasonably accurate at low frequencies. The long-term behavior is basically right. Okay, so we've got this relative error bound that we're going to exploit here. So now let's come back to kind of our feedback loop. We've got kind of our classical controller. We now have a model where we've got the design model with a description of how much model error there is. Our recursive least squares, then we've got an estimator. This estimator has built into it what the kind of design model is. That's kind of hidden in here. And the recursive least squares is then going to try to figure out, with this FIR filter, what do we inject here? Okay, now this piece is time varying because we keep updating the coefficients. So I'm going to call this kind of this entire block here M, and then the LTV. It's just some block from W hat to V. That's time varying because these coefficients keep getting updated by the recursive least squares. So now what I'm going to do is, this is maybe a pretty standard robust control trick, which is I'm going to extract out through just some kind of block diagram manipulation the uncertainty and the time varying part of this recursive least squares. Everything else down here, which involves the nominal dynamics, the nominal controller, the estimator, that's all linear time invariant and known. Okay, so this is just a bookkeeping. Let's separate the stuff that's hard to analyze from the easy stuff that's linear and time invariant. And the question is, we want to ask is, if I do this, if I tell you a bound on how much model error there can be, and I know what this recursive least squares is doing, will the closed loop be stable? This is like a robust stability type result. So this is the main kind of technical result, which is you can turn this into a type of scaled small gain condition, which is, it depends on kind of the pieces that are down here, which again depend on the nominal plant dynamics, your baseline controller, and your estimator. And the condition is, it says something like the following: assume I've normalized the uncertainty, assume I put a bound on the linear time varying part, that bound is beta, then I can still prove that you're going to be stable even with this uncertainty if you can show that some induced norm condition is satisfied. So this P is just some induced norm. Typically in robust control, you use P is equal to 2. So you use the induced L2 norm. This then looks like a scaled H-infinity condition, or what's called the structured singular value. Here we're going to use P is equal to infinity, and there's a whole textbook on this particular case. This is going to be useful because when I talk about the implementation online, this will be a particularly useful norm to use. And the reason why the case of P equal to infinity is useful is if I can tell you what this bound should be, and I want to bound this operator is changing at all points in time, it turns out I can just implement that at each point in time. I can just be bounding the coefficients. Okay, that's the basic point of this fact. So here's what the implementation looks like. We first offline determine how much uncertainty there is in our model. We apply this scaled small gain condition, which turns out to just be a convex optimization. We found a bound on the FIR filter coefficients for which we can guarantee stability of the closed loop, even though there's this uncertainty. Then online, what we do is we run recursive least squares, we figure out what these FIR coefficients are, and then we project them back into this set. And by projecting them back into this set, we're able to prove that you're going to be stable even in the presence of this model uncertainty. So we're going to sacrifice a little bit of the performance, because if the FIR filter coefficients are outside this set, we're projecting them back into a set for which we know we're stable, but we're at least able to guarantee stability. Okay, so then maybe a little more details online. At each time we solve the recursive least squares, we get the optimal coefficients. Turns out, based on those optimal coefficients, you can figure out the signal you're injecting in, and then there's basically a simple limiter that limits the size of that optimal injection. You can think of this as like a version of like a control barrier function or like a safety filter. So let's maybe just wrap up and just show how this kind of performs on this simple example. So we'll come back to this simple plant model with the controller, the disturbances we had before. We're going to use recursive least squares to figure out what this optimal injection should be. But then we're going to use this kind of safety filter to limit the magnitude of this injection to ensure that we're robustly stable. The amount of uncertainty that we're going to add, we put a very small amount of uncertainty here in this kind of perturbation to the plant model. This level is consistent with the deviation that I had in the earlier example. We apply this scaled small gain condition, and it says we should restrict the FIR gains to be in a set that's defined by this kind of constant. We chose something slightly smaller. Anything less than that is actually fine. What does it look like when we turn this on and off now? When there's no model error, here's the output versus time. This is, again, with the classical controller. That's exactly the same as before. So we reduce the effect of the disturbance from 1.18 to a variance of 0.27. When we turn it on, okay, there's a little bit of the noise left. This isn't quite as good as what we got before because we're using the safety filter to slightly limit the effect of the recursive least squares, but it's still quite small and close to the noise floor. Then we select 100 random plants that are in this kind of uncertain set. We rerun the simulations. Again, this is with the recursive least squares off. So this is just with the classical controller. Again, basically the same performance as before. Now, when we turn the recursive least squares on, we remain stable for all the plants. And we do a better job of canceling out the disturbance. So you can see the standard deviation of the output now is still pretty close to the noise floor. There's 100 samples here, so these are the min and max values. So there's a couple cases that are worse than the others. But at least we can ensure that we're not going to go unstable. We're not so sensitive to the model error. This is maybe just kind of summarizing some of those results. The basic idea is when we add the safety filter, the performance on the nominal model is close to the performance without the safety filter, much better than the PID controller. When we run this on certain plants, we now remain stable as opposed to the case without the safety filter, and we're still doing much better than the PID controller. So we're slightly sacrificing some performance. The variance here is slightly larger than without our safety filter, but we're making sure that we're robust to model errors. Okay, let me wrap up so I have some time just for questions at the end. Again, the basic idea was to try to use online optimization. And here we're using online optimization to learn the disturbance and try to cancel them out. And again, the applications that we have in mind are high precision kind of applications, satellite pointing being one of them. And our implementation was really trying to think about how can we ensure that we're robust to small model errors, with the idea being that we don't think the model errors are things that are so easy to learn, as opposed to the disturbances, which have learnable or repeatable features. And so our way of doing that was to develop a robust stability condition. And in particular, it's developed in a way that we can just enforce that in real time on the optimizations. We run the recursive least squares, we project the solution back to the set. And I did all the examples with the recursive least squares, but any type of online optimization, you can think of this as giving you like a set to project onto. And the projection set is just ensuring robust stability. All right, with that, maybe I'll pause here and just see if there's any questions. Thank you.
Thank you, Dr. Seiler. I think we'll wait for some time for the questions to pop up. But meanwhile, I have questions. So,
Sure.
yeah. So understand, like, as much as I understand, like, you have this uncertainty set, and then within that uncertainty set, you would want to guarantee that uh, you're precise and you're canceling or like you're at least minimizing all the disturbance effects other than the white noise components. But maybe it's not for this application, but what if you're learning about a system online, and you let's say I'm looking at it more of like a Markov decision process, and in an MDP, like, you may you may only know so much about the transition function or like dynamics. So it's like each state action, next state transition is gonna come with a probabilistic guarantee based on how much you explore the system. So I'm just wondering if these uh, probabilistic uncertainties can be incorporated, or like how would that play a role in such systems
Yeah,
if it
that's a great question. The formulation would be completely different because here it's discrete time or continuous time. So the action space is continuous. And I think you formulated things where maybe there's discrete action spaces. The closest thing I can envision is if the plant is um, a Markov decision process on a discrete space, there's a transition matrix. Imagine that transition matrix had a part that's constant that you could learn. And then every time it had another part which is small that kept changing. And that's the part that you couldn't learn. That could happen in lots of cases, right? Where there's really a part that's pretty consistent across time that you're trying to learn, but there's a part that's just it's changing
yeah,
a little bit.
yeah,
That's how I would think about it. And I actually don't know when if you were to do the learning in that situation. The first question I would ask is if you assumed that the Markov decision matrix was constant and you developed a learning algorithm, how sensitive it is to variations that are kind of the small perturbations changing at different points in time. And if it is sensitive, then how do you make it robust to those variations that are maybe not so easy to learn? Because if it's changing at each point in time, there's not it's you whatever you've learned up till now isn't necessarily going to be a predictor for what's going to happen.
yeah.
That's how I would think about it. But the tools would be completely different than what I've presented. But I think it's an interesting question.
Okay, thank you. There is one question so far, like how do you select the number of FIR coefficients? It's from Panos Konatides.
Yeah, that's a good question. I guess the best way to answer that is that's telling you almost how much history you want to have built into into the part. Again, this is recursive least squares, but any part of the piece that's doing the learning, the n or the number of coefficients is telling you how far back in time are you using kind of your estimate of the disturbance. I guess if you knew like what the harmonic frequencies were in the disturbance and you knew what the sample time, you could try to pick n so that you've gone back one or two cycles of the disturbance. Now, as you pick n bigger and bigger, then obviously at some point you're hitting computational or memory limits. But at least that gives you a way of saying, I'd like to predict what this extra input should be based on a couple cycles of what I think the disturbance might be doing.
Thank you.
I think in our example, we just chose n. We didn't do that type of analysis. We just chose n after a couple iterations, just seeing what worked well.
Thank you. Uh, there's one more question. So when it comes to, like, let's say convincing NASA about like they require high precision controls, and uh, what does it take to convince NASA to use a particular algorithm? All of these things, let's, maybe from an economic perspective.
There's two pieces. I think it's not just NASA, like space and also the like commercial aircraft have very stringent requirements. The commercial aircraft side more driven by, passengers and lives are at stake. And then in space, there's a huge financial impact if you do something wrong. I'm more familiar on the commercial aircraft side. There's all sorts of requirements of like the probability that this is going to fail is 1 out of every billion hours or 10 to the minus 9. So that drives you to things like three separate computers are implemented to do the flight controls. Each computing box has three separate processors that like no chip flaw in any one of the chip lines is going to bring the airplane down. So you get lots of redundancy built in, which I haven't talked about here. But the algorithm itself, generally, there's all sorts of requirements on the proofs of stability, gain in phase margins, like things that we maybe teach at the undergraduate level that you should not be very sensitive to modeling errors. And so that's one of the things that they're concerned about, not just with like online optimization, but doing neural networks in the loop or any type of optimization that's what you may call like black box, as opposed to a classical algorithm like very simple PI controllers, which is well understood. I know exactly what it's going to do. I would say these are unanswered questions. So NASA and the European Space Agency actually have an ongoing series of workshops to try to study what are the, like, how do we prove that these algorithms are going to work? What are the right kind of requirements? And the same, like they're going to have to be different, but analogous to what we are, do for conventional controllers. And I think the reason they're studying that is they actually do believe that there's benefits to these, non-traditional methods, neural networks, learning-based controllers, optimizations. I mean, you can see that in sort of like SpaceX, like the launch vehicles, where then they recapture the capsules. There's a huge economic benefit to doing that, and they're using versions of online optimization to do that. So I think we're going to start seeing more of those things. But I think the questions of like how do you do the safety proofs, that's not completely answered.
Thank you.
Yeah, I think it's a good question and a great point.
I think that's all the questions that we have for today.
Okay, great.
Thank you
All
so
right. Well,
much
thanks
for
for your time, and thanks again for the invitation.
Yep. Thank you so much for joining us, and hope to see you sometime in CDC. Hopefully.
All right. You too.
Yeah.